Welcome to The Explainer. Today, we're diving into the invisible engine behind modern AI. It's this amazing technology that lets machines actually get the meaning of our words. This is the secret language powering pretty much everything from chatbots to search engines, so let's get right into it. So we ask AI to do all sorts of things. Write, summarize, even just chat with us. But have you ever really stopped to think about how it actually understands us? I mean, how does it get the nuance, the real meaning behind our sentences? That's the big question we're going to answer today. And the answer, it turns out, is something called a text embedding. Now, this isn't just some nerdy technical detail. It is the absolute bedrock, the foundation for so many of the AI tools that we find so impressive. And the impact is huge. I mean, embeddings are the engine behind semantic search. Search that understands concepts, not just keywords. They let AI classify text without a human looking over its shoulder, and they even give models like ChatGPT a kind of memory. Seriously, it is almost impossible to overstate how important these things are. So how does this whole secret language thing actually work? Well, the very first step is all about translation. We have to turn our human language into something a computer can actually process. Look, at its core, the problem is pretty simple. The sentences you and I write, that's just unstructured text, and it's totally meaningless to a computer. To make it useful, we have to translate it into the one and only language that every machine understands, the language of math. And that translation process, it's called embedding. We basically feed our text into an AI model, and what it spits out is a special numerical fingerprint that captures the text's unique meaning. This fingerprint is just a long list of numbers, or what's technically called a vector. Now, here's where the magic really happens. You can think of this list of numbers, this vector, as a set of coordinates. And just like that, we can plot every single piece of text onto a giant multidimensional map. And on this map, distance means something really special. The closer 2 points are, the more similar their original sentences are in meaning. But what do we actually mean by similar? Well, it really depends on what we train the model to care about. On the left here, we could train for semantic similarity. The model learns that a dog is playing is really, really close to an animal is having fun. But on the right, we could train for sentiment instead. So now, I love this movie and this film was incredible are mapped right next to each other because they share that same positive feeling, even though the words are totally different. Okay, that all sounds pretty cool. But how does the model actually learn to build this map to begin with? How does it figure out what similar even means? Well, the key idea here is that models, a lot like us humans, learn best by comparison. To really understand what something is, it really helps to understand what it is not. There's this great little story that explains this perfectly. A reporter asks a famous bank robber, "Why do you rob banks?" And he just answers, "Because that's where the money is." Now, technically, he's not wrong, but he's totally missing the point. The reporter wasn't asking, why a bank instead of a grocery store? They were really asking, why rob a bank instead of, being a law-abiding citizen? It's the unspoken contrasts that gives the question its real meaning. And that idea right there, that is the heart of a really powerful technique called contrastive learning. We teach the model what something is by showing it what it's not. We don't just show it a picture of a dog, we show it a dog, and we also show it a cat and explain why it's not a cat. Okay, so here's how that works in practice. First, we start with what's called an anchor sentence. Then we give the model a positive example, a sentence that means pretty much the same thing. And here's the crucial part. We also give it a negative example, something different. The model's entire goal, its whole job, is to tweak its own internal map to pull the anchor and the positive closer together, while at the same time actively shoving the negative one as far away as possible. Now, there are a couple of ways to get this done. The older methods, called cross-encoders, would look at two sentences at the same time to decide how similar they were. This was super accurate, but also incredibly slow. The big breakthrough came with a newer approach called a bi-encoder, or SBERT. It's way smarter because it creates an embedding for each sentence on its own, independently. This makes it lightning fast and easy to scale up, which is exactly what you need if you're searching through millions of documents in the real world. All right, so that's the theory, but how does all this actually work in the real world where data can be messy or, you just don't have that much of it? And here's the big catch. To train one of these powerful embedding models from scratch, you need an absolutely staggering amount of data. We're talking more than 1 billion pairs of sentences. For most people, most projects, that's just not going to happen. So what do? I mean, What if you have a great idea for a project, but you've only got a few thousand really good labeled examples to train on? Is it game over?
No, absolutely not. Because there is this brilliant trick called augmented SBERT. Here's the game plan. First, you take your small, precious, human-labeled data, your gold data set, and you use it to train one of those slow but super accurate cross-encoders. Then, you just let that expert model loose on a giant pile of unlabeled sentences and have it label them for you. This creates a huge machine-labeled silver data set. And then finally, you combine both your gold and silver data sets to train your fast, scalable bi-encoder. You've basically just used a tiny bit of quality to generate a whole lot of quantity. It's genius.
And how well does it work? You won't believe it. It turns out that by using this method, you can get to nearly 99% of the performance you'd get with a massive, fully labeled dataset, but with only about 20% of the initial human effort. That is a game changer. It makes this powerful AI so much more accessible to everyone. Okay, but let's push this even further. What if you're starting from scratch? You have 0 labeled examples, not a single one. Now what do? This is where something called unsupervised learning comes in, with a really elegant method called TSDAE. It's kind of like giving the AI a puzzle. You take a normal sentence, and then you damage it by just randomly deleting a few words. The model's only job is to put it back together, to reconstruct the original. And the thing is, for the model to be good at this, its internal embedding has to have captured the full, complete meaning of the sentence. It literally teaches itself the meaning of language just by fixing broken text. So, from learning by comparison to these clever data tricks, we've seen how AI learns to map our human language. This is a huge deal. It's about way more than just better search results or smarter chatbots. But it leaves us with a really important question to think about. If an AI learns what things mean based only on the examples we give it, what happens when the examples we give it are biased?